This tissue can be classified as gray or white matter depending on whether there's myelin. If there is, it's called myelinated, and that is white matter. Only the axons will ever be myelinated. If they are, it's light in color, so it makes the tissue look whiter. That's why we call it white matter. When you have myelin, you can send messages quickly. So it's used for things like getting a message from your toe up to your spinal cord so that you can react to stepping on a nail or something. Or getting quick messages out to your muscles to contract. Gray matter is other parts of neurons, so dendrites and cell bodies, and axons without myelin. This is used for all the integrative areas, and you'll also have some unmyelinated axons when either it's not important for the message to go quickly, or when you kind of want to send two messages. An example of this is if you stub your toe, you get the immediate ouch, and then a little bit later follows on this kind of throbbing pain. You've got myelinated and unmyelinated axons carrying that message. The first one tells you something happened, check it out. And then the second one kind of reminds you that the damage is still there. Questions on gray versus white matter? We also have both kinds in the brain and spinal cord, and we'll talk about where they are when we get to them. Neurons can be classified by their structure, which is how many projections or axons and dendrites they have, and by function, which type of communication they carry, sensory, integrative, or motor. Our categories for number of projections are 1, 2, and a lot. They're called unipolar, bipolar, and multipolar. Out of these, only one can ever be an axon. So anything it has past that is going to be dendrites. Multipolar are the neurons you see most often drawn. They have lots of dendrites connecting to the cell body, and then one axon. That axon may branch a fair bit and communicate with multiple cells, but there's only ever one place that it connects to the cell body. One axon to it. So this is a multipolar neuron. Multipolar neurons are located partially or completely in the central nervous system. So all of your integrated neurons are multipolar. So are your motor neurons. Typically what happens with a motor neuron is the dendrites and cell body are in the CNS, and then the axon goes out to the effector. So if you're tall enough, you could actually have a neuron that's that size. It could go from your spinal cord all the way down to your toe. Bipolar neurons have two projections. It's one axon and one dendrite. They connect to opposite sides of the cell body. Bipolar neurons are always sensory. By the way, you can tell axons from dendrites on these if you look closely. Some have come out, but there's little knots in the axons, or at least there used to be, that were supposed to be the synaptic knobs. They've all come out. Oh well. One dendrite, one axon. 1 + 1 is 2, bipolar. Specifically, they're used for what we call special senses, which means something that you detect only with a specific organ in your head. So you'll have bipolar neurons in your eyes, ears, connected to your taste buds, and so on. A unipolar neuron has only one attachment to a cell body. That might beg the question, okay, it has one. Is it an axon or a dendrite? It is an axon. The dendrites, instead of connecting to the cell body, connect directly to the axon. The cell body's just kind of sticking off to the side, where it has a nucleus for making proteins and whatever else it might need to do. Unipolar neurons are also sensory. They're used especially in the sense of touch, where the dendrites pick up information from your skin or some other locations. They connect to the axon, which goes all the way up close to your spinal cord, or where all the cell bodies are grouped together. It makes a bulge in the nerve called a ganglia. And then the rest of the axon delivers the message to the next neuron in the pathway. So that's unipolar. And the one we already had up here is multipolar. If we tie that together with our functional classification, sensory, sometimes you'll see them called afferent neurons. Afferent means going into something, so in this case going into the CNS, but sensory is easier to remember. Sensory neurons have the input, and they will be unipolar or bipolar. Interneurons, this is a contraction of integrative neuron. They're the processing neurons. And then motor neurons are the ones that take the messages away from the CNS. Motor is sometimes called efferent, which means coming out of something. If you need to remember afferent and efferent, which you will when we get to the kidneys, think A for arrive, E for exit. Interneurons and motor neurons are both multipolar, where clusters of cell bodies in the peripheral nervous system are called ganglia, singular ganglion, and they don't really do anything. It's just that those cell bodies have to be somewhere to manage the cell. In the central nervous system, we have clusters of cell bodies that may have some complete interneurons in them as well. Those are called nuclei. Nucleus is such a useful term that we've used it for so many different things. You've got the center of an atom, the membrane that holds the DNA in a cell, and now you have clusters of gray matter. Any questions on neuron types? At the synapse, you have two cells that come together. The presynaptic cell is always a neuron. It's the one that brings a message to the synapse, and it'll be its synaptic knob that meets the other cell. The cells don't touch. there's a little bit of a gap. I'm going to draw this like it's a dendrite. This will be the postsynaptic cell. So the postsynaptic cell receives the message. And then you have the synaptic cleft, the little gap between them. On the wide view, we just see a couple of synaptic knobs coming up to this cell. When you look closer, you can see the gap. Now, I've got a model neuron here, which is useful for looking at Schwann cells, dendrites, and it cuts off the axon, but it has a whole bunch of synaptic knobs from other axons attaching. You can't see the synapse there either, because to get it to stay, they had to actually glue them on. So we've already looked at one synapse, which was the neuromuscular junction. What was different there was that the postsynaptic cell was a muscle instead of a neuron. Postsynaptic cells can be any cell that the neuron needs to communicate with. Questions on structure before we start looking at the electrical signals. Electricity in your wires is basically electrons running along, going from metal atom to metal atom to get out the other end. That's harder to do with nonmetals and potentially dangerous in living things. So we have to do electrical signals a different way, and that's with ions. All cells have a difference in ion concentration and charge that's called cell membrane potential. We say that they're polarized because they have different charges in different places. Like a magnet is polarized with north here and south there. The cell has negative here, positive there. The negative is on the inside of the membrane, positive is outside. So when the cell has this difference, it's called polarization or resting membrane potential, because that difference is there when the cell's not even doing it. Our electrical impulse or action potential comes from letting ions move to change these charges. The most important ions in membrane potential are sodium and potassium. This is where you'll have to start recognizing their symbols. Na for sodium, K for potassium. The little plus is there to indicate that they've given up one electron, they're positive. Potassium is much more concentrated inside the cell, with less outside. Sodium is much more concentrated outside the cell, with less inside. And all of your cells have that difference. Some of them, it just sits there and stays that way. Others, like neurons, use it by letting the ions move. If you think back to chapter 3 and concentration gradients, if the sodium's more concentrated here, where does it want to go? Yep, the sodium wants to go inside where there's less of it. The potassium, on the other hand, is more concentrated inside, so where does it want to go?
Outside.
Outside. So if we let them move, they take their positive charges with them and it changes this membrane potential. Now, to get these ions in different places in the first place, we have to use active transport, that process for pushing things against their concentration gradients. There's a specific protein carrier called the sodium-potassium pump. It pushes 3 sodium outside the cell and trades them for bringing in 2 potassium. And it has to spend ATP to do it. That's how active transport works. You need some source of energy. Now, you notice something about the math?